Hello, Mr. Lopriato here, and we are looking at AP Chemistry. We are looking at some of the basics of bonding. So in this video, we are looking solely at Lewis structures. All right, Lewis structures are something you should be familiar with. You should have already seen that for the main group on the periodic table, we can draw out dots to represent the number of valence electrons. So something like a group 1 metal like lithium would have 1 dot. Carbon, a group 14 element, would have 4 dots, and something like fluorine, a group 17 halogen, would have 7 dots. All right, anytime we see 2 dots together, we consider that a lone pair, and lone pairs do not bond. All right, look at our noble gases. They have 4 lone pairs, so they are not typically going to be seen bonding, right? And that is why they have that nickname, the noble gases, right? Because they do not interact, whereas something like fluorine or chlorine are going to be very reactive because they want to get or share to get that last electron, right? They have 7, they want 8. So we're going to see a number of structures. You should have already seen a bunch of these. You should be familiar. We can see a couple of different things happening. This is our period 2. All right. So these steps, the guidelines, anytime you are given a chemical formula, the first thing you want to do is count the total valence electrons in the molecule, right? Each atom is going to contribute as many valence electrons as it has. And if it is a polyatomic ion, we are either going to add however many electrons for the negative ion, or we would actually reduce electrons if it was a positive polyatomic ion. All right, then we're going to try to arrange the atoms into a skeleton molecule. Typically, we're going to try to figure out a central atom. That is most often the less electronegative element. All right, typically there's only one in the formula, especially for simpler compounds, and typically it's first in the formula, although none of that is a guarantee. So we have to be flexible here. Step 3, we're going to connect all the atoms with single bonds, right? And we can represent a single bond as a set of 2 dots, but a dash is going to be simpler, it's going to streamline it for us, and it is going to be better for us. All right, then we're going to distribute the electrons to give every element an octet. All right, the only element that doesn't get an octet is hydrogen. Hydrogen and helium kind of abide by the duet rule. All right, now this idea of the octets, you may have learned about the octet rule, and in a lower level chemistry class or a middle school science class, you might have been like married to that idea, right? Every element has 8, there's no exceptions. Well, in AP chemistry, it's more like the octet is a guideline. It's where we start, but it's not necessarily where we're going to end up. A lot of elements actually can violate the octet rule in both ways. It can have less than 8, and it can have more than 8 very easily. Only a couple of those period 2 elements are really going to follow the octet rule. So it's not a good rule, but it is a great guideline. All right, so you're going to give every element an octet, and then the last thing you're going to do is you're going to double check your count of electrons. If your count of electrons match, you are good to go for drawing your Lewis structure. If you have extra electrons left over, you are just going to throw them onto the central atom. All right, if you have extra electrons left over, it should hopefully be in an even number, and you're just going to add as many lone pairs to the central atom until you've used up all of your electrons. And if you're using too many electrons, which is the most common issue when we go to recheck, all right, we are going to form a multi-bond, and I will show you that trick. It reduces the total number of electrons by 2. All right, so let's get some examples going. All right, let's try CH2O. First thing we do, we count up the electrons. Carbon contributes 4. Hydrogen contributes 1 valence electron, but there's 2 of them, so we're going to multiply it. And oxygen contributes 6, right? That gives us our grand total of 12 valence electrons. That's what we have to work with. All right, we're going to settle on a central atom. Carbon is first in the formula. It's not the lowest electronegativity. Hydrogen is lower, 2.4 versus 2.1, or 2.5 versus 2.1 roughly. All right, but it's first in the formula, so that is a good tip for us, right? And hydrogen can't form multiple bonds because of that duet rule. All right, so let's attach the 2 hydrogens by a single bond, right? We are filling out the skeleton structure, and let's add the oxygen, right? So now we need to give every element an octet. All right, but we don't have to give the hydrogens octets. They are satisfied. But we're going to put two dots on the carbon. Those represent 2 more electrons because each bond is currently representing 2 electrons. So now carbon has 8 around it. Oxygen is going to need 3 lone pairs. All right, now oxygen is satisfying the octet rule, and again, it's a guideline. Okay, so now we want to recount. We want to recount the valence electrons, right? Each bond is representing 2 valence electrons, so that gets us 6 electrons in this picture, and each lone pair represents 2 electrons. So when we add that all up, we have 14 electrons. All right, that's too many. It is too many. We are only supposed to have 12 electrons to work with in CH2O. So here is the lone pair trick, and this will reduce 2 electrons. All right, you want to find 2 adjacent lone pairs, right? The carbon and oxygen, they're right next to each other. We're going to take 2 adjacent lone pairs, and we're just going to eliminate them, right? They are gone. So it's definitely when you're drawing out these structures, you want to be doing this in pencil because you may be changing stuff. All right, and what we do instead, because now carbon and oxygen don't have their octets, now we're going to add in a double bond. All right, and if we were to recount, the double bond is now representing 4 electrons, 2 sets of 2 electrons being shared. All right, and when we do the recount, we get 12 electrons. So this is the Lewis structure for CH2. We can feel good about that. We went through our 5 steps. All right, how about something like IF3? All right, we're doing the same thing. We're counting the electrons. 7 valence electrons from iodine, plus 7 valence electrons from each fluorine atom, but there are 3 atoms, so we got to multiply it. All right, that gives us a total of 28 valence electrons. We want to settle on a central atom. Iodine, less electronegative. First in the formula, less number of atoms. That is a good choice. All right, we're going to put the 3 fluorines around it. We are going to connect them by a single bond. All right, we're going to satisfy the octet rule for iodine by giving it 1 lone pair, right, bringing its total count of electrons around the iodine atom to 8. And we're going to give 3 lone pairs to each of the fluorine atoms. Right, when we go to recount, remember, our bonds are 2 electrons, our lone pairs are 2. So if we think of just the single fluorine, it has 8 electrons around it. So 8 around all 3 fluorines, that's going to get us to 24 electrons, plus the lone pair on iodine, we're going to end up with 26 valence electrons. But we had 28 to work with. So we're going to add an extra lone pair on the central atom. We're just going to stick it on there, right? This is what we're going to call an expanded octet. Iodine has more than 8 valence electrons, which is totally fine, by the way, and this is what it looks like. And you might not be happy with the way they look, so maybe you're going to erase them and you're going to redraw them just to make those 2 lone pairs a little bit neater, a little more evenly spaced out. Totally fine, not a big deal. All right, but this is IF3. Our last example, NO3 minus, the nitrate ion. All right, polyatomic ions are excellent practice for drawing Lewis structures. So that is where I would recommend you try your practice if you're trying to get this skill down pat. All right, nitrogen, 5 valence electrons. Oxygen, 6 per atom, 3 atoms, and 1 extra valence electron because it is a -1 polyatomic ion. When we add that all up, that means we have 24 valence electrons in nitrate. All right. Central atom, we're going to go with nitrogen first in the formula, lower electronegativity, and there's only 1 of them in the formula. So all of that helps us be confident. We're going to put the 3 oxygens. We're going to give the central atom an octet. We're going to give the outer atoms octets. The only element we won't give an octet to is hydrogen. Again, because hydrogen follows the duet rule since it's such a small atom. We're going to recount. All right, bonds represent 2 electrons. Lone pairs represent 2 electrons. We should be good at this skill of counting electrons. We're going to see we have 26 valence electrons. All right, we're only supposed to have 24. So we're going to have to do that lone pair trick, right? We're going to identify 2 adjacent lone pairs, right? They're on 2 separate atoms, but they are next to each other. We're going to eliminate them. We're going to put the double bond in its place. That lowers our electron count by 2, so that brings us to 24. this would satisfy all of our 5 steps. This would be almost done, would be the Lewis structure. Right now, what we need to make it correct for the polyatomic ions, for the negative ones, we want to put brackets around it, and we want to put that -1 charge outside, right, representing the charge of the polyatomic ion. And you may be asking yourself, why did I choose the right oxygen? No particular reason. I could have done the left oxygen. I could have put the double bond there instead and removed that lone pair. And I could have even done the bottom oxygen and removed that lone pair, right? All 3 would be valid. All right, and since all 3 are valid, this gives us the idea of a resonance structure. All right, a resonance structure is when the double bond can be in different spots, right? There's always a single bond between all 3 of my structures. That never changed. It's just the placement of the double bond. All right, you don't have to draw the resonance structures. I just wanted to make this video to show you the steps to draw any valid Lewis structure, which you should be able to do if you follow those 5 steps.